Old man using technology. Watch out. So we talked about, I think the thing that would have been most new or unknown to most of you guys was the idea of degree. Maybe? Do you all know, basically have some idea, at least now hopefully, of what a polynomial is? Can somebody give me an example of what isn't a polynomial?
Straight line.
No, straight line totally is. So watch this. What's a polynomial? You ready? What's a polynomial? Here's an example, 5. 5 is a polynomial. What's something that... Sure. So not a polynomial would be a square root of x, right? That's not a polynomial. Later this semester, we're going to learn that square root of x is actually x to the 1/2 power. Did anybody know that already? Very quickly, since I put that up there, why does that make sense? How do you do like the square root of 9? What's the square root of 9? 3. If I told you that you just cut 9 in half multiplicatively, does that make sense? Why is the square root of 9 3? Because 3 times 3 is 9. So take half of that is 3. Yes. So if you cut 16 in half multiplicatively, wouldn't that be 4? Because 16 is 4 times 4.
Yes.
So what's a fundamental part about square roots is somehow cutting it in half multiplicatively. So a half in the exponent, and exponents are based on multiplication. Holy shit. But that's later this semester. Why do I want to write it like that? Because what makes something a polynomial? All the variables in it have whole number powers. Not a whole number. What about, I'm writing it here, so I'm already giving it away. 3 over x plus 1. That is not a polynomial because it has an x on the bottom. And again, later we're actually going to learn something on the bottom, like 1 over x, is a negative power.
Could pi be a polynomial?
Hell yeah, all that. Square root of 7. Those are the weird ones. Any constant is automatically a polynomial because, now stay with me guys. Isn't 5 equal to 5 times 1? And what's 1? X to the 0. Does the variables in this expression have a whole number power? Yep. So that's why every single number is technically a polynomial. Because all the letters that a number has in it is raised to a whole number power. Yes?
For any number, it's a polynomial. But for variable, it's not.
Exactly. This is not a number. It's a variable to not whole number power. It's not a polynomial. And again, you guys, we should be able to answer this. Well, let's see if you can answer this. We've done this before. What could x not be? Is there something x can't be here? Negative 1. Why can't x be negative 1? Because it makes
0.
the bottom 0. What can x not be here? Do you guys know? What kind of numbers can you not do the square root of? Negative numbers. A polynomial is supposed to work for any x. So this restriction of it can't have something that's not a whole number power. It can't be on the bottom. It's because then there would be values I'm not allowed to use. And a polynomial is supposed to exist everywhere. The domain is supposed to be all real numbers. Oh shit. So that's why when I say to somebody, I've got a polynomial, the other person knows I could use whatever input I want to. Yeah.
So like square roots and anything that's negative can't be.
Cannot be polynomials. Yeah. You're welcome. All right. So, something else we talked about yesterday was just adding polynomials, and that really is just adding like terms. To make the problem a little more interesting than the ones we had on the page, can you add anything here together? Let me ask you this.
Oh, yes.
This first term, how many A's does it have?
2.
And how many B's?
1.
1. Is there another term that has 2 A's and 1 B?
No.
Is there another term
Oh. No.
that has A squared and B? Isn't there?
Oh, yeah. This is bad.
So just because I wrote it out of alphabetical order doesn't make it not like terms anymore. If I have 5 A squared B's, and this is minus 5 A squared B's, I just wrote it out of order. I remember once, so if I write this, so you guys see how this, I'm writing the same exact thing. Why is that the same? Because when I multiply two things, it doesn't matter. Is 7 times 8 different from 8 times 7?
No.
No. So is B times A squared different from A squared times B? No. I remember one semester, I think it was the second semester I was teaching, somebody was just really like, that is different, Jeff, you have changed. And I'm like, oh my God. I did all these examples and she just wouldn't believe me. And I thought, what have I got myself into? Are you guys okay with this? That's the same
You literally
thing.
just take the A and you just add it with the other A and you usually, not add it, but compare.
Yeah, just
Yeah.
swip.
Switch them.
Or you just notice what makes things like terms. Same letters, same amount of each letter.
Yep.
So they both have 2 A's and a B. So if I put these together, what happens to them? They die. And I can put him in alphabetical order just to... That's why alphabetical order is the conventional way, so then it's easier to identify like terms quicker. All right. Some of you guys look angry. I'm going to chalk it up to the temperature. Okay. Can't be the math. Now, let's do the second problem. Let's do this one. P of y equals -3y squared. This is the next level stuff here. Let's just do this one. What's P of -2? How would I do that? Yeah, you replace all the y's with -2. So please let function notation be simple. It's just substitution. So -3 times -2 squared plus 4 times -2. Yeah, and then it just becomes a problem.
And then
It should be negative.
Good, good. So this is -3 times multiplication happens after. So you're right. I always see somebody put this down on the next step.
Oh, and not.
That doesn't make any sense. How did you make 2 6s out of 2 2s and a 1 3? You can't do that shit. Do you have to think of it that way? No. Order operations save your ass always. Exponents before multiplication, right? So -3 is just sitting there waiting. What's -2 squared? 4. Then you multiply. I like it. And then you got -8, -5. So you get -12, -8, -20, -5. Owe me $25. Aha.
What is the P one is pretty easy.
What's
The
up?
first one in on the example.
What is it, sir?
The first one on the example.
P of 1, yeah, just plug that thing in. So you should get negative. Where -2 come from? Yeah, so if you do P of 1, I did these out of order, but P of 1 would just be -3 times 1 squared plus 4 times 1 minus 5. So it'd be -3 plus 4 minus 5.
Yep.
-3 and -5 is -8 plus 4 is -4. All right. So I can change the numbers, but the process doesn't care. You just do what it tells you to, the computation, once you put that value in. Let me see. Okay. And then the last thing here is, what do I have to be careful about on a problem like this? I don't want to write all this shit down. 5x squared plus x cubed minus x, I think it says. Minus negative 5x squared minus 4x cubed plus 3x. Yeah. Left myself noted. You guys see the problem on that paper? It's the very last problem on that front page, front side. What do I have to do first?
You gotta get a distributive.
Distribute the negative.
Yeah.
Because I don't have a 3x. I have a negative 3x. So I don't know what I have until I distribute this thing. So then I get 5x squared plus x cubed minus x
5x plus 5x
plus 5x squared
plus 4x.
plus 4x
Minus.
cubed, sorry.
Yeah, I would say that.
So see how I moved it over to be with the like terms? I lost my poor little cube here.
Minus 3x.
Minus 3x. And then you just put your like terms together. So you get
I need to put it in order, like.
no. This just happened to line up nicely. You don't have to do it like this. You can put it all in one big line and then underline. But you can also see the utility of lining up your like terms. So I just want to show you, you could do this if you want to. So then I get 10x squared, 5x cubed.
Minus 4.
Now if you stop there, it's fine. What's one little thing you could do to make it a little bit more conventionally correct? No, we're not factoring anything yet. Why would I put that first? Because it's highest degree. Yeah. But if you just stop here, you're fine.
Why don't you add the like x 2x's plus 2x's? Why isn't it 4x's?
All right, because it's not. It's 5 of these
Right.
plus 5 of these.
Okay.
How can that be 10 of those?
I mean, there's 2 of those x.
Now watch.
right?
What's this mean? I got 5x squares, right?
Yeah.
And if you add 5 more x squares, what do you have 10 of?
10x squared.
10x squares.
Yeah. But there is 2x squared.
But again, what is this based on? What operation is this based on?
Yeah, I know it's right, but I'm just like trying to.
So it's based on what operation? Multiplication. So x squared times x squared is x to the 4th.
Alright.
Because then you're collecting, but this is 2 x's,
Yeah.
and I got 5 of those. This is 2 x's, I got 5, so I got 10 2 x's. I got 10 x squares. Yeah. You can only change exponents when you are multiplying things with exponents. Yeah.
But so if you're adding, so like 5x plus 5, was it 5x squared plus 5x squared, you just add the bases?
No, you add the numbers, 10x squared.
Yeah, that's what I'm saying, the base, the 5.
The coefficient.
Yeah, the coefficient.
The base is x. Yeah.
Yeah.
And it really just is. I got 5 of these plus 5 more of these. I got 10 of these. You wouldn't say I got 5 chairs plus 5 chairs. I got 10 elephants. Yay. I mean, it's a silly example, but I can't fundamentally change what I'm counting as I count them. 1 person, 2 gnomes, 3 giraffes, 4. It's like, what? All right, that was too silly, but 2 gnomes. You guys get that? I mean, really, that's it. That's how that works. Just coefficients are keeping track of how many of these. Okay. So, the one little thing I want to do today, and then we're going to let us out of here a little early. I don't know if anybody came in late, but check your email. We're going to have different rooms next week. And hopefully the week after that it's going to be. I'll keep an eye on the forecast, and I'll get rooms for the next week if it's still going to be hot. 'Cause I don't think they're going to fix the AC this semester.
Awesome.
Nice.
Yay, Grossman, way to think ahead. Oh shit.
Because you said that yesterday.
Hey, dear President. Fire me, try it. Like he watches. What, somebody was asking something?
Yeah.
Okay. Yes. We're nowhere near there yet. Yeah, we haven't even started that site yet. So let's catch up to you. All right, here's the little bit I want to do. Oh, good.
It's, 'cause, 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 'cause,
Remind me, how do you do this? Yeah, you distribute it.
4x minus 28.
Cool. And you guys, I showed you earlier semester why. I showed you earlier why distribution works. You should be on one level. If you forgot how this works, you should be angry when you first see this, because the same jackass, namely me, that's been saying you must do order operations. I suddenly go, oh yeah, it doesn't matter. Because what should you do technically order operations? In here.
Solve x minus.
So then you would be not quite correct, obviously, but if you said you can't do anything because I can't even do the first step, how do I get around it? I write x minus 7 4 times. And then it's just collecting like terms. So I rewrite the problem so I can attack it a different way. So I'm not breaking order operations. Can't. Maybe. So, nothing new there. So the first level of this is just to pile more shit in this thing. So like if I had 4x squared times x cubed minus 3xy squared. The fundamental thing I apply, the fundamental process doesn't change. I'm still going to take this thing and distribute it. It's just I got to be a little more careful. I got a little bit more going on, right?
So that's 4x. That's 6. Is it 6 or 6?
I like
Yeah.
So watch. Guys. If you need to, especially when the stuff in here starts getting more and more complicated, there is not a damn thing wrong with doing this. I have to do this times this, so let me write it out and not do it yet. You guys got it with me? Right? Because how do you distribute? You take this times the first thing, bam. Now you take this times the second thing. And then next step is you can worry about what this is. Now what do you do here? Add them. Why? Because this is 2 x's in a chain linked to another 3. So there's 5 total. And again, this is where I go a little crazy and I say there is no 2 or 3 in this term. There is no 2 or 3. There's 2 x's, 3 more x's, 5 x's. This is 4x to the 5th minus 12.
X to the 4th?
No.
Dang.
What's being squared here? Y. This is x to the first, right? X times x squared is now 3 x's, and the y dude doesn't change. Do you have to do this step? No. You can go there, 4x5, bam. Negative 12, x cubed, y squared. You don't have to do that step. But this step is really useful if you're not 100% confident with what you're doing. Yeah.
So the reason the y doesn't change is because we're not multiplying any more y's.
Yeah,
to
we're not
that.
giving it any more y's.
Okay.
I like it.
So what I wasn't understanding before was that the form from the x is a coefficient and that the x is the base. That was what
Okay.
I was confused
I like it.
So when you're adding and subtracting, it's basically like combining the like terms, and when you're multiplying, it's adding the form?
On the like basis.
Yes.
So just like with adding, subtracting fractions versus multiplying, you don't need an LCD because they don't have to be like terms. Addition and subtraction is much more like uptight. They have to be exactly the same. Multiplication, they don't have to be exactly the same, but they do have to have like basis, for example, to put them together, right? Is that, you guys with me on that? Yes. So the level of likeness is less for multiplying and dividing. Addition and subtraction, they gotta be exactly the same. Yes, ma'am.
So what you're saying is when you multiply, so say like on the second video it says 10p squared times 5p cubed.
Yes.
So I would just add the exponents, I don't multiply. I just
Exactly.
multiply the regular.
Exactly. And to be really honest, let's see if you guys can. So if I had 9, yeah. What happened to you? Weren't you just working? Oh God. That sucks. So if I had 9, there you go. 9 times 27. You could do it, right?
Yeah, I can do
Well, what
it.
is 9? 9 is 3 squared. What's 27?
243.
Yeah, there, Jeff. I'm thinking of 3 cubed, right? And now you guys see what I was just thinking. 3, the result should be 3 to the 5th. So if I rewrite numbers as bases to powers, now just check me. Who's got the calculator? What's 9 times 27? Let's see if you can beat me.
It's
243.
Yeah.
Okay. Good try. And what's 3 to the 5th power? I don't know if you know where your to the buttons
3
are.
times 3.
Yeah, you can do it
3
that way.
times 3 times 3. Hey, look, it's 243.
So this came up last time, but I want you to realize, why does it seem as if we treat variable multiplication different from number multiplication? Because numbers are not written in the same form. They're not going to have the same process then, are they? So again, I purposefully did that. There's a 2 and there is a 4 in this problem, right? So 2 times 4 is 8. There is no 2 and there is no 4 up here. Does everybody understand what I mean when I say that?
That's just telling you how many times you have to put x, multiply.
Exactly. There are 2 x's, 4 x's. There's no number 2. There is no number 4. So if you put an 8 there, it doesn't make any sense. If I got 2 x's in a row, link on 4 more x's in a row. How many x's do I have in a row? 6. Now this is supposed to be 8, right? But kids, I write 4 as 2 squared?
Mm-hmm.
What's 2 to the first times 2 squared? 2 to the third, which is 2 times 2 times 2? 8. Yes?
I'm just a little bit confused, so that would be 9 to the 5th, up top.
Oh, good. All right.
But because
I'm ready.
you did 4 times 3 on that one.
I totally did, because am I writing these in exponential form? No, I'm actually multiplying 3 times 4. When I write something with an exponent, what does this mean? There are 2 3's that need to be multiplied. And then I multiplied them with 3 more 3's that need to be multiplied. So how many 3's total do I have that need to be multiplied? 5. If you think the answer is this, I'll say to you, where the shit did you get 5 9's from? I don't see 5 9's. I see 5 3's. So when you write exponential notation, you are keeping track of how many multiplications you eventually have to do. You're not actually multiplying shit yet. The bases stay the same. Even with numbers, because again, I'm collecting how many 3's I have to multiply by eventually, right? So I can't suddenly say, 3's, now I've got a bunch of 9's. No, can't do that.
So the base is what's being multiplied in the.
The base is what's being kept track of. I have 2 of them.
No, what I'm saying is threes are the ones being multiplied, and the exponents are the numbers telling you how many times they're multiplied. The base.
Yeah, okay. Yes.
So on the sheet, it's 10p.
All right, let's do that one. That one's come up a few times now. Let's try that one. So the first problem on the other side, what was that again? Sorry? 10p squared,
5p cubed.
5p cubed. So I know 10 times 5,
Yeah.
50. And then p squared times p cubed, how many p's? Yeah.
Well, see, now you're multiplying them, so now I'm getting.
Multiplying what?
The 10 and 5.
I always do.
But you can do it on the 3. I don't know.
No, okay,
Never mind.
stop. So the earlier problem I had was this, 9 times 27, right? And I made it 3 squared times 3 cubed. All I was trying to show you there was, I know this answer is 243.
So. but-
Stay with me. I know it's 243. Any other way I write the problem to get there has to end up at a number that means 243. If I write numbers in exponential form, the properties of powers work.
But if the 9 times 27 wasn't above that, would you do 3 times 3?
Oh, no. That would be that, no matter what. No matter what.
Okay, so.
Because I got 2 3's times 3 more 3's. So how many 3's do I have now? 5. That's it. So again, if I wrote this out, what's 3 squared mean? 3 times 3. What's 3 cubed mean? 3 times 3 times 3. So how do I rewrite that? 3 to the 5th. The only thing I did this for was to show you, this is the way we've always multiplied. If I have a different way to write the problem and a different way to do it, it still has to come out to what we know it should. Or else we throw all the math out and go home. Right? That's the point I was trying to make.
No,
But,
I get your point, I just,
but for example, 7 to the 4th times 7 to the 11th.
I'm 17.
She's confused about the coefficient and the base. That's what she's confused about. She's confused about why you have to multiply. Why are you multiplying the coefficient and the 5 and not?
Maybe. Is that what it is?
Yeah, the coefficient.
All right, wait. So,
You're
no.
multiplying
It
to
shouldn't
10
be.
to 5, but you're not
Because I
multiplying
know
to
how to
10.
do 10 times 5. And I know how to do p squared times p cubed.
So you're saying if it has a like base, then you maintain the same base and then just.
So let me ask you this. All right, I did this problem before. If I had to do this by hand, I would choose to do this times this first because it makes 10. So I can multiply a string of multiplication any order I want to. In this case, it's because it makes it easier. Then I got 10 times 21 is 210. Bam! Right? And you can do that at parties, kids.
Lane party.
Lane parties is exactly what I was thinking. Like a party I would go to. Now. A problem like this, the question isn't what makes it easier, the question is what makes it possible. I can't do 10 times p squared at all, but I can do 10 times 5, so I do it.
What if that 5 was a 10, would it stay 10 and then 5?
All right, so if it was this problem, is that what you're asking?
Yeah, would it stay a 10?
No, because what is 10 times 10?
Then that's why I don't understand when you change the 3 over there.
Now watch, you ready? So one way to do 10 times 10 is it would be 10 to the what? What do you do with the powers with like bases? 1 plus 1 is 2. And then this would be p to the 5th. What is 10 squared? Okay. So can we accept that I'm not going to suddenly start doing numbers, rewriting them and doing exponent rules, because I don't need to. But if I did, they would act just like variables do. The only reason it feels like we do two different things is because they're written in two different ways. If I did write them and use properties of exponents, it would eventually get to the same place. But I don't need to. What I'm trying to show you is people always get confused. They start doing stuff like they make this 15 p to the 5th. And you see what that person is thinking? Suddenly they think everything is addition. No. Or I get 50 p to the 6th. What do they think? Well, 2 times 3 is 6, Jeff. If you try to tell me different, I'm going to... Jesus.
It was what she was confused about is the coefficient and the base.
No, I know. I'm just trying to figure out how to explain it. But, again, are you cool with the fact this is all multiplication, right? So maybe if I do this, can't I rewrite this like this? Because multiplication, I can multiply in any order I want to. Isn't 4 times 3 times 5 the same thing as 3 times 5 times 4? It's the same number, right? And now this is a problem I know, and this is a problem I know. P who? 5K. But I'm just trying to get you to the point where you don't have to do this, because then we're going to start getting more and more shit here, and if you're taking time doing this, that's bad. So for example, I don't know what the second problem is on there, but here's the problem. This is the second problem. Not good enough. All right. Actually, yeah, maybe it is good enough. All right, 3xy cubed times negative 2x4y squared. Shit. Equals 50. Aw. So I want to get you to the point where you can look at this problem, you tackle your numbers, 3 times -2, -6. And then you do the letters as they come. X times x to the 4th,
X to the fifth.
x to the 5th. Y cubed times y squared.
Y. And that's it.
Yeah, and how do I know I'm done? There's no addition, no, and I've already combined everything, there's nothing more to do. I can't combine anything further. Maybe.
I got it, this one, you look at boxes.
Oh, that's coming. Yeah, we're building our way up there. Okay. So, we're all cool with the basic distribution law. I think this is the last thing we'll do. The next level to this, I'm going to show you something. I'm not sure how to think. That I really don't necessarily want to show you, but it's good to see it at least once. So, for example, and actually this is the box dude. I kind of like this guy. See x plus 3 and x plus 4. This box dude is actually kind of nifty little box dude. Nifty little box dude. Let's see. Oh yeah, that's the 4 side, and that's the 3 side. I'm gonna do it. All right, let's do it all over. Do you guys agree with me that this side is x plus 3 long,
Yes.
and that side is x plus 4 long? So what's the area of this? That. How can you get, like if I wanted to get the area of this house shape, couldn't I get the area of the square times the area of the, I mean not times, but plus the area of the triangle?
Yes.
So one way to get the area of this whole thing is to get the areas of all these and add them. So what's the area of this little box here? X squared. Is that cool?
Yeah.
Now think about this one. Let's label some more stuff. How long is this side? X. How long is this side? 4. How long is this side?
3. X.
All right. What's the area of this little box?
3x.
What's the area of this little box?
12.
12.
Yeah.
Let's see here.
4x.
So what's the whole area supposed to be? X squared plus 3x
4x.
plus 4x plus 12. And then of course you can, so the next, yeah, but real quick, whatever this is, better be this, or else the whole thing is shit. Right? So how do I look at this correctly? I have no idea if any of you directly use the